Good afternoon. It's great to have you all here. It's a great turnout. We're very excited to be showing you the incredible research that our students are doing here in the Paul G. Allen School. I'm very excited to introduce our lunch speaker, Siddhartha Srinivasa. Sid grew up in India, went to IIT Madras, where he majored in mechanical engineering, actually, had a sudden desire to live in Pittsburgh. Did his graduate work in the Robotics Institute at Carnegie Mellon University, receiving a PhD in 2005, and became a professor in the Robotics Institute at CMU. Also worked at the Intel Research Lablet, creating a robotics group there at the Intel Lablet in Pittsburgh. He was also named the coolest person in the robotics school in 2012, which I think is a really exciting credit to his name. Sid has done incredible work. He basically does all levels of the stack, builds robots. Sadly for him, his robots are more famous than he is. But over the last year, we started talking with Sid and got really excited about him. And luckily, he got really excited about us in Seattle. And we're incredibly lucky and honored to have him here in the Allen School. Sid Srinivasa.
Thank you, Hank. Hello, everyone. I'm Sid. It's nice to meet you all. And like Hank said, I just moved after 18 years at Carnegie Mellon University. I build robots like this. So the last time I gave a lunch talk was to my son's kindergarten class. So I know it's not going well if you start weeping loudly or start throwing food at me. But I have really lots of experience giving talks like this. But thank you all for coming. Today I'm going to talk about robots. Like Hank mentioned, I work on robots. I work on literally nothing else but robots. And I get robots to pick stuff up and put them back down. Robotic manipulation, physical robotic manipulation. Turns out that's really hard for me. And possibly for a lot of people, and that gives me a lot of job security. And today I'll tell you a story of how I got into human-robot interaction, about how humans and robots can work with each other, and some of our sort of algorithms for enabling robots not just to perform tasks seamlessly and efficiently, but also to perform those tasks with and around us. Like, we would all like to have robots that not only make food for us, but can actually sit down and have lunch with us and enjoy a meal. And so today I'll talk a little bit about some of the algorithms behind human-robot collaboration. So I want to start off by acknowledging my group. This was the last picture we took at Carnegie Mellon University before we all left. So everybody here left, and they're down here out on the first floor and the ground floor. So it's really exciting to be here. And this is our robot, Herb, as Hank said. Herb was, just last week, he was in Vancouver shooting for a secret TV show that I can't talk about, that I absolutely love, that I'm sure you do too, in science fiction. But I hope you're not recording this. No, you are. OK. Yes, so Herb is a robot that we built from scratch. He's a robot that physically manipulates objects in the world. If you come again anytime, you can come down to our lab and see what he does. And today I'm going to tell you a little bit about what he does. So I work on robotic manipulation. That's literally the only thing I do. Manipulation is something that I'm really fascinated by because we seem to be performing manipulation tasks effortlessly. You know, just the act of eating food is such a magical task. You're manipulating deformable objects right in front of yourself. You're dealing with a handover, a complex handover process of taking that food and shoving it into your mouth, itself another deformable robot, while engaging in a conversation with everybody else. So you're engaging in social dialogue. You are amazing. You've done really well. And not only that, you know, my kids can do it, and they learn to do this better. Right? So it's really fascinating. And That's what's most interesting about manipulation, is that even the seemingly mundane task of putting food in your mouth is actually intricately complicated and detailed when you're trying to turn that into an algorithm that needs to go into a robot such that it can figure out how to do these tasks autonomously. So really, a lot of my work is on being able to transfer this effortless insight that we have to physical robotic systems, turn it into algorithms and theorems that we can prove such that our robots can do this too. So here's, in terms of food, here's perhaps one of my most prized videos. This is a commercial that we shot for Oreo. And the story of this is that Oreo called me 2 weeks before this video was shot and said, we'd like you to come by and try to separate the cookie from the cream. Apparently, this is a big deal in America. And we said, challenge accepted. We will do this completely autonomously. So we wrote an Oreo detection algorithm. We wrote motion planning and control algorithms that can actually pull the Oreo apart by their fingernails. If you actually worked with these WAM arms before, you know how hard that is. And scrape the cream off of that cookie. And what's really exciting is that we never built this robot to separate cookie from cream. Actually, the Oreo is the most sensitive and delicate object that we had ever manipulated. But we were really excited by the fact that the building blocks of autonomy that we had built, of perception, of planning, of control, machine learning, were such that we were actually able to transfer the ideas, the algorithms, to this fairly delicate and really complicated object. Also, our failures were delicious, so which is really nice. And truth in advertising, this only succeeds about 3 out of 10 times. So the Oreo problem is still wide open if any of you are interested in funding me to work on this. But it's really also a testament to the fact that robots, what we want to build are general purpose robots. If you ask me to build a robot that could separate the cookie and the cream of an Oreo, I would be able to build you a much, much, much better robot than this. But what we want is for a robot like Herb to wander around in an environment that it's never seen before and perform tasks with objects that it was really never designed to manipulate, right? And that's really what we want, is for our algorithms to be able to generalize well enough that they can deal with these kinds of objects. Continuing on the topic of food, so I'm also really excited not just about manipulation, but manipulation with and around people. Right? One thing I realized, this actually happened about 6 or 7 years ago, where we were trying to deploy some of our robots actually out in the real world, and we realized that the real world has this one very, very pesky attribute, which is it's filled with people. And we started off by treating humans as obstacles that needed to be avoided. People are obstacles, we avoid them. And it turned out that if you treat humans like that, then they start behaving weirdly with you. And we realized that people were actually offended and sometimes behaved in ways that were incredibly strange to a robot because, like they said, the robot was ignoring them. So the fact that you have a robot that's sort of doing its job, ignoring humans, can actually potentially be detrimental for this sort of seamless collaboration. But like I said, what I really want is, this is my favorite chef, Jacques Pepin. He's on PBS. And every once in a while, he gets his daughter to hang out with him and cook with him. And she's a novice. She doesn't really know how to cook. And they have this wonderful interaction of him teaching her how to cut things, her working with him and trying to learn the art of cooking. And I would like it to be the case where when my robot rolls into my kitchen to perform a meal for me, I don't have to evacuate the kitchen. I would like to be able to cook seamlessly alongside my robot, right? And that actually requires a pretty deep understanding of how robots and humans can actually work together. I think we all agree that that requires us to treat humans not as obstacles that must be avoided, but as agents, as reasoning, rational entities that need to be collaborated with, potentially even manipulated and coaxed into doing what you want them to do, right? And what I would like to do is build a formal theory of how humans and robots can collaborate with each other. So, and the applications are very broad, right? So we've been looking at applications of shared autonomy. We work with patients with high spinal cord injuries, where we put robot arms on their powered wheelchairs and enable them to perform complex tasks that they would not be able to otherwise. We also work at shared workspace collaboration, where a human and a robot are working together to solve a problem. Right? So the applications of enabling humans and robots to work seamlessly together is very broad. But really, the driving force for me for the past several years has been in trying to answer this question of, can we build a unified mathematical model that can really explain and understand human-robot collaboration? Because if we build that unified mathematical model, then we can apply it to shared workspace collaboration, we can apply it to shared autonomy, we can apply it to a whole broad set of tasks. This is a question that will take generations to answer. It's a very, very broad but open question. But what we would like to be able to do is take fundamental steps towards answering that question such that our robots can work closely with humans. And this has actually spawned my whole sort of family tree. These are my students who are now all faculty at various places, as well as I'm an academic grandfather now. I have a student now who's a professor at Stanford, and a whole bunch of really exciting work. And today I'll highlight one or two of those works. So I also want to start off by saying that human-robot collaboration was the genesis of robotics. So this is a video from 1952, a very, very long time ago. Right? And this is one of the first robots that was actually deployed in a real environment. This is a robot that was in a nuclear plant that was meant to deal with hazardous nuclear waste. Right? And you can see how dexterously and beautifully it's actually performing these tasks, because there's a remote operator on the other side who's helping the robot perform these tasks. And I think this was sort of a huge step for robotics, because people looked at this video and people looked at this demonstration and asked the question, how can we automate this process? Right? How can we actually make this something that can actually work all the time without the need for the expert operator? So a lot of robotics actually stemmed from this desire to get humans and robots to work seamlessly with each other. So coming back to this mathematical model, I'll go 4 slides into a little bit of math. This is when you start throwing food at me. There's a generalized idea of reinforcement learning, where the idea is that you have a robot that's interacting with the world via its actions. So it's a very simple model. The robot performs some action on the world, and the world spits out a new state as well as a reward or a cost. It says, you did well or you did terribly. The robot absorbs that reward and that new state, and then continues to perform its next action. This is what we do, potentially, as stochastic optimal controllers that we are. And what we would like to be able to do is come up with a policy that will optimize our long-term reward. We have some reward that we get at every step. We would like to optimize some long-term reward. And this is a very standard reinforcement learning paradigm, where there's a robot that's interacting with the world. Humans complicate this, right? A human is someone who is also interacting with this world that this robot was until now so happily interacting in, right? The human shows up and he's like, well, I want to make food too, so I want to join you in making this food. So the human also pushes in their actions into this world, right? And now what happens is that the reward essentially becomes the joint reward of the human and the robot, given the human and the robot's policies, right? Where we've expanded the state space into this cross-product space of the robot and the human. Now, if the human and the robot shared the same brain and knew everything about what each other was doing, then this problem is identical to the previous problem. It's just that the robot is now split into 2 entities, a human and a robot. But therein lies the problem, which is that the robot often has no clue what this human is doing, right? The only way it's able to understand what the human is doing is by having some sort of subjective prior that maybe they're a rational agent. Maybe they do things somewhat rationally. And by the effects that they have on the world. So the robot's like, does he want to make coffee? Oh, he's moving towards the coffee filter. Perhaps he does. I'm going to change my policy based on that, right? So the partial observability of the human's intentions and the human's policy complicates this quite tremendously for the robot. If the human and the robot just sat down and exchanged policies with each other, then everything would be great. But that's something for the future. And so that's what we are trying to get our robots to do, is to get into the minds of people and try to figure out what their policies are, such that the robot can then take its own actions to maximize this long-term joint reward. Right? So it's an interesting problem of exploration to understand what the human wants to do, and exploitation such that you actually maximize your joint long-term reward. And so the sort of key insight for us was this idea that human-robot interaction is really an underactuated dynamical system. It's a blimp that's floating up in the air, and the human is like the wind that blows on this blimp. The robot's desperately trying to control this blimp, and every once in a while, the human blows on it, and it's like, oh, this is perhaps what the human intends to do. So maybe I will build a model of how the human is blowing on me and react accordingly, right? And sort of to take this analogy further, now that I'm in Seattle, I'm contractually obligated to show you this picture. This is me every day going to work, if I knew how to swim. So the actual analogy is that you think of the robot as this guy on a paddle board. Is this a paddle board? Yes. See, I know this so well. On a paddle board. And that's the robot. And what the robot is trying to do, or this person is trying to do, is trying to predict what the sea is going to look like, or the lake is going to look like. So they're looking at the current behavior of the lake, and they're trying to make a prediction of the lake's actual future behavior. And then run a controller. They're running a closed-loop controller that maximizes some long-term reward based on the prediction, right? So this is sort of standard reinforcement learning. What's really, really interesting is also the fact that the robot can not only change its own policy, but it can influence the sea, right? So here, what human can do, what's happening here is that you're creating these wakes, not so that you can optimize your current reward, but so that you're setting up for future rewards. So you're manipulating the sea such that you can set yourself up for future gain. So you can influence the sea in a little way, but you can certainly influence it such that it actually assists you much, much later on, right? We do this all the time. When we work with someone, we sometimes do things for them, not just so that we can optimize our reward, but in anticipation of far future reward, right? We do things, we say, oh, I'm going to help you out with this, not for now, but so that I can set you up so that you can trust me, such that much later on I'll ask for you to do something else for me, right? And so that's the beauty of human-robot collaboration, is this sort of long durative influence that's possible with these systems. And really, the mathematics of HRI can really be concisely described by this tight loop. There's this tight loop between prediction, control, and influence, and you just want to keep looping this over and over again. So let me give you one example. So I've been working with patients with high spinal cord injuries. This is actually some of our work deployed on a real system, working with patients who are out there in the field. So this is a robot that's helping. This is Seb. He has MS, and he's using a foot-mounted joystick to control this robot arm. And controlling these arms is incredibly hard, even for an expert user like me. Right? It's a 6-degree of freedom arm that you're trying to control with a joystick. But imagine someone with a disability, an upper extremity disability. It's maddening for them to control. So a lot of our work is on trying to see if we can use our robot's intelligence to alleviate this problem. How can we enable our robot to help people control robots in a way that is seamless for them? Right? And this is sort of some of our successes with this. So just to formalize this, the typical paradigm for teleoperation is that the user controls a robot to achieve some goal. It could be either with a brain-computer interface, or it could be with a joystick. And this is incredibly noisy, insufficient degrees of freedom, and really, really tedious. Like if you ever come to my lab and try to control a robot with a joystick, it's maddening. Even for me, after 18 years, I find it really hard to actually control a robot with a joystick. Our paradigm was slightly different. What we wanted to do was not to directly assist the human, which is sort of the robot acts as a puppet that's moving its arms based on the human's directions, but to understand their intentions, right? We want to be able to understand why you're moving the arm in a way you're trying to move it. And if you can understand the why, which is actually a much lower dimensional space than actually understanding how to control the arm itself, then we can potentially assist the human in performing that task. So if the robot knows that you're trying to pick up a coffee mug, and it actually has an algorithm for autonomously picking up the coffee mug, then it can actually help you with it, right? And that's the fundamental idea, was instead of looking at shared autonomy as transfer of control from a human to a robot, think of shared autonomy as a caregiver, as someone who's trying to understand your intentions and help you with performing the task. And so we want to simultaneously predict and assist. So the mathematical formulation is that the human wants to pick up that yellow block. They're a stochastic optimal controller. They're noisily optimizing some cost function, and so they have some policy for doing that. The robot doesn't know which of these objects the human is trying to pick up, because the robot doesn't know your true intentions. But given each of these true intentions, it knows how to solve the problem. So the game that the robot that is planning to play is it's trying to divine your intentions while simultaneously helping you perform the task, because the latent state, the state that it doesn't know about, are your intentions. And you can formulate this as a partially observable Markov decision process, where the latent state are the intentions of the human. And you can actually optimize for this. So the true optimal function is to minimize, under expectation over all of the possible intentions the human may have, your reward, your long-term reward. Turns out this is actually fairly intractable when you have continuous state, continuous actions. But there's this very cool trick called hindsight optimization, which we did not invent, but we used, which is about determinization via hindsight, where you're trying to solve one uncertain problem as a summation over many, many deterministic problems. It swaps the expectation and the min such that you get a lower bound on the true value. And once you do this, then the basic idea becomes as follows. So the human thinks about moving towards a particular goal. The robot updates its value function based on that, and then it uses hindsight optimization to then update the expectation over its beliefs. It solves the POMDP online. So as it is learning more about your intentions, it's assisting you based on the confidence of its prediction. The more confident it is about any particular goal, the more it is able to assist you. And this actually ends up being really beautiful. So here on this side is a robot that's trying to assist you based on max probability. It's looking at what you're doing and saying, this is probably the best goal you're trying to go after, so I'm just going to go straight towards it. And this, well, it's already finished, is our hindsight optimization, which is trying to maximize expectation under all of this uncertainty, right? And that actually works really, really well, because the hindsight optimization algorithm essentially says, I don't know whether you're going here or here, but I do know that going straight is going to help with both of them. So I'm not going to hedge my bets on left or right until the very end, right? And that actually falls out naturally out of the framework. And this is a demonstration of how we implemented with a patient with a BCI, a brain-computer interface. So there, we're decoding their neuronal output using actually a machine learning algorithm, and using that to control a robot arm to pick up objects. So the algorithm itself is very general for that. And this is actually a problem that we're looking at right now. I talked about feeding and eating, about how it's a really fascinating problem. It turns out that this is the #1 need for the patients that we speak with. And so they said, we would love to have a robot that can actually feed us. And so we said, sure, why not? It's a fantastic research problem. And we get to eat broccoli, which is nice. But it is a really, really challenging problem of being able to manipulate deformable objects, and also of the social interaction between a robot and a human, of how and when to feed. You don't want a robot that keeps shoving food into your mouth. You want a robot that understands the cadence of human dialogue, of human needs and wants, and so we're running facial recognition algorithms, gesture recognition algorithms to try and understand what human intentions are, so that we can feed them just when they want to be fed. And this problem is actually infinitely more complicated, right? Like I have a 6-year-old and a 3-year-old, and I spend a lot of my time trying to feed them, mostly unsuccessfully. And so you can think about feeding as a caregiver as not just the process of getting food into somebody's mouth, but also coaxing, cajoling them into eating what you want them to eat, right? So if your child doesn't want to eat broccoli, I feel like all children hate broccoli for some reason, but at least our children do, then you have to coax them into eating it. Imagine being able to build algorithms that can automatically do that. And this is very, very similar to rehabilitation, where you have to not only help a person perform a task, but also enable them to do this by themselves. And we actually did this. This is a study of various policies, and the top left policy is the one that we developed with hindsight optimization. And we're actually here using a gaze tracker. So the user there is outfitted with the gaze tracker, because gaze is another wonderful form of intention, right? You often gaze at what you want to do or what you want to do next. But gaze is also, at least natural gaze, is also infinitely complicated, in that sometimes you're gazing at other things. Sometimes you're gazing at the robot. Sometimes you're gazing at your hands. And so you don't want the robot to think that all of these are your goals. So a lot of our ongoing work is on being able to harness natural gaze, just the way we look at each other naturally, to understand human intentions such that we can enable robots to assist them to perform tasks. So I want to wrap up by sort of coming back to this picture of just this tight coupling between prediction, influence, and control, which really, to me, is at the heart of human-robot interaction. Mathematically modeling humans as stochastic optimal controllers using Bayesian reasoning to actually produce robot policies means that we can marry stochastic optimal control as well as a whole history of work on POMDPs and MDPs into this really interesting and qualitative problem of how does a robot understand who you are and what you want to do? How does a robot develop your trust? How does it understand your intentions and assist you? So we're really excited about bringing about this unification between the qualitative aspects of human-robot collaboration and the more mathematical aspects of stochastic optimal control. And this is the question that I hope that we will be able to answer at some point of building one unified mathematical model for human-robot interaction such that we can enable robots and humans to work seamlessly with each other. Thank you.
Thanks, Sid. We could take a couple questions if people want, and then we will start the next session at 1:30. So let's take one or two questions if people have them. Sorry. Questions? Anybody find an error in the formulas that Sid presented? OK, then we'll let you grab a last cookie. Oh, was there one? Go ahead.
Sid, can you talk a little bit more generally about why you decided to come to the UW, how many grad students you brought here, and what you hope to accomplish long term?
Oh, thank you. I didn't expect that question. I was going to talk about POMDPs, but I brought everyone. I had the single largest lab at the Robotics Institute at Carnegie Mellon University. Everyone decided to come. There was one student who was graduating. He's actually graduated, and he's moving now. So it was a very large number of students, and I'm really grateful to Hank and Ed for enabling that. I think that's been really fantastic. Why I decided to come? That's a very, very long answer. I think I'm really excited about UW. I think that I spent 18 years at Carnegie Mellon University. I have 250 roboticists there, the biggest robotics institute in the whole world. I had the biggest lab at that biggest robotics institute. But I think I was really excited about making impact. I wanted to make true impact. I wanted to be interdisciplinary. Sometimes when you're so large, you sort of tend to be in your own little silos. What I love the most about UW here and the computer science department is the fact that it is truly collaborative. Everybody says that they're collaborative, but when I came here last year, I truly felt that it is collaborative. And also, I would love to build bridges between the computer science department and the medical school and biomechanical engineering and all of these other departments that are just a stone's throw away. Like back when I was in Pittsburgh, I was collaborating with the Rehab Institute of Chicago. So I would fly to Chicago every month so that I could work with them and fly back. I want to do that by just walking over to my collaborators out here in the School of Medicine. So I'm really excited about being here. I'm also honestly very nervous. I've only lived in 2 cities before, in Chennai for the first 19 years of my life, and Pittsburgh for 18 years. So I hope I won't disappoint people. Thank you.
Thank you. OK, let's thank Sid again. Thanks for coming, and enjoy the next sessions. We hope to see you as well at the poster session this evening. Thank you.